All right. Thank you so much for inviting me, for the organizers. So today I'll be revisiting a talk named Till Recollapse. It's especially useful for those that are starting to look into more mature targets in bug bounties, basically. So in this talk I'll be explaining basically how to find weirdly simple but impactful bugs on such targets. This is a longer version of this talk with a few more examples. So thanks for the intro. I think I can skip this part. I'm Baptista, also known as OXACB on Twitter, HackerOne, and so on. So for today, we'll be discussing some quirks about regex and in general input validation and how these can be bypassed. Then we'll moving on into the Recollapse technique. And finally, we'll be visiting some real-world examples. So it all started a few years back when I was doing bug bounties for live hacking events with HackerOne. And some friends were like, okay, there's some sketchy functionality here on this host. If we can bypass some certain whitelist, we can eventually leak a token. And that was what exactly happened. So we figured out a way to bypass a certain validation, and the way I was able to do it led to all this research. So it all starts with the user input, right? So modern web applications rely on validation of user input. Good for us when it doesn't, right? And it uses, of course, regular expressions, which is something that not even most developers actually understand as they write these regular expressions. So this is just an example. AA.com doesn't match these regex that is meant for an email address, but the second one will return a match object, in this case in Python. But also, of course, sanitization of user input and the way it's rendered in the output of the web applications. For example, the HTML special charged function will sanitize to HTML entities this dangerous input. And also normalization, which is not so well known, let's say. And we have different behaviors in different programming languages in terms of the output that it produces by default, okay? So if we have these Unicode characters like this, A-I-O-U, it will actually convert that weird ordinal indicator into degrees, D-E-G, down there in Python. And up there we have, in this case, in PHP, you see the behavior is even more weird. So all these can lead to very interesting scenarios where your input somehow gets normalized, and then you can eventually, if they are blocking, for example, single quotes or double quotes, in the first case, you can see that if this input gets normalized somewhere, you'll be able to eventually pop some impactful issues even on very mature targets, because this is not so well known. This is simply a normalization table that is available on the GitHub for this tool, Recollapse, that I launched it was like 1 year ago. So basically, I was able to build this table by matching characters that will normalize to the base characters that you can see up there, which are the regular ASCII characters. So there are some problems with validation of user input. I was already telling you that regular expression is not understood by people that actually copy-paste these regular expressions. For example, Stack Overflow, people used to go there. Now we are using more and more, especially developers, GitHub Copilot and so on. So here's a regular expression to match for an email address. Sure, it's very secure, right? Not really, because it will accept, in this case, email addresses like the second one that you see here, okay? So most of these developers, especially these developers that work on very, very large corporations, They don't actually go to regex 101, for example, to test the regular expressions, or sometimes they don't even write proper unit tests for it. And sometimes they actually copy-paste these regular expressions from other projects. Let's say that you have a subdomain for this company, and they are using a certain regular expression there to validate an email address. But then on another application, for example, in a mobile application, the regular expression will not be the same most of the times, because it's a different developer, and it's very hard to have the same regular expressions on the code base. In the case of modern tools, such as GitHub Copilot, for example, powered by OpenAI, this was a function generated dynamically by GitHub Copilot, and in the description, in the prompt, we say, okay, check if the URL is a subdomain of the domain provided, okay? So it generated this regular expression, and it seems like LLMs are not very good as humans in terms of regular expressions. So as you can see, all these examples will go through this code. It's very interesting that the last two go through because of the dot, because the actual domain is, in this case, formatted directly into the string, and you have example.com in this case. So the dot that you see in example.com will not have a backslash, okay? So in this case, it will be possible to have the last two examples. Those will go through this regular expression generated automatically by GitHub Copilot in this case. And it's very interesting that in my research, I was able to understand that not all the base libraries for programming languages in terms of regular expressions have the same behavior. So the $ asserts a position at the end of the string, for example, or before the line terminator right at the end of the string. So this is very confusing if you read it, but basically it should mean, in my opinion, that, okay, we'll have a regular expression with a $ in the end, and this will mean that the string ends there, but we can have a new line in the end, it will still match, right? The thing is, like, when you look into JavaScript, for example, it will match only if you have this regular expression, you have a $ asserting the end of the string there, but JavaScript will only match the first example with 3 A's in this case. And if you put a new lines or any new string, a string after the new line, it will not go through the validation. In Python, it's almost the same, but the third example will actually go through. So Python is basically following what the convention about this $ means, at least in my opinion, or the developer that coded the base library for Python. And in terms of Ruby, it's even more interesting because the fourth example will go through with another string in the end. So basically, this means that if we can just send a request and put a new line or any other character, white space characters, for example, by default, I'm not talking about these new line or multi-line flags that we can put in the regular expressions as well. By default, they will have, in fact, different behaviors. So this is something that is not very well known by the developers and good for bug bounty hunters and hackers in general, that we can still find some very weird bypasses with this technique. This is just a table resuming this regular expression example regarding the $ that asserts the end of the string. So there's some sort of confusion on implementing regular expressions in the core library. So regular expressions are hard. So let's talk about the technique that I've been applying to these mature targets, and it's very, very simple. It's about somehow redefining the impossible, because let's say that you have a very tough user input validation, you cannot put any payload there, You have an URL, it is super whitelisted, you have an SSRF scenario, and you cannot put, like, you know, internal hosts. Like, how can you actually redefine this almost impossible validation? And at the same time, how can we also leverage user input transformations in terms of what I was talking about, normalizations? And basically, the answer is about fuzzing the parameters, pretty much how we do in binaries, for example, with basically AFL or other tools, but in a smart way and in a fast enough way for the web. So if we start with the initial scenario, we just need to send unexpected inputs, lots of them. We are poking into a black box, and basically we are going to get a weird behavior back. And this black box, this simple, very simple concept, but it will start shining some light about the behavior present in the back end of the application, about the source code that we do not know. So the idea about this initial scenario is, okay, we are going to just send a lot of possible inputs, and in this technique is all the possible bytes in multiple positions, like I'm going to show you after, to see if any request actually goes through or at least results in a different behavior. So the technique is very, very simple. It's focused mostly on regular expression groups, okay, to defeat these kind of validations. And basically, we have the starting and termination positions to check if the regular expression has the starting and the dollar sign in the end. We have the separator positions, which are usually around punctuation characters or special characters. And then we have normalization positions, which are basically all the characters that can be usually normalized. The idea is about fuzzing positions with all the possible bytes and analyzing the responses. So these are just some examples of these pivot positions. So a regular expression can be asserting the beginning of the string, or it can be asserting the end of the string, or they can even be not asserting anything at all. And you can have an URL, and if they are not asserting the beginning of the string, you can have anything that you want before the actual URL. It will still match. And in the end, the same thing. Then we have the separator positions around special characters. This is because usually, for example, letters are part of A to Z regular expression group, and then you have the actual characters being present in the regular expression. And then you have the normalization positions. Vowels work better in a lot of libraries, but obviously any character can have Unicode alternative representation. So these are just some examples, but basically the idea is to fuzz all the positions with all possible bytes, but in a way that this doesn't explode in terms of complexity. So we are not going to fuzz all the possible combinations of this. We are going to fuzz one by one and check the behavior and iterate multiple times over this. So these are just some examples with usernames, with even HTML to find new bypasses for XSS sanitizers, for example, and so on. So this is a tool that is available on my GitHub, and it's a tool capable of generating such inputs, and it supports multiple fuzzing sizes and encodings. And it's basically a tool not meant for actual fuzzing, but to generate this type of inputs. So let's just jump to a quick demo of the tool. So let's say that we have this example. This is just a demo application. So let's say that you are a bug bounty hunter, you approach this application, and this application will allow you to log in to another application as an identity provider, for example. So the behavior is it will use your session, it will go to an x.example.com with a token. Okay, so let's try to understand how this works. So we click yes, we intercept the request, and we can see that we have a URL parameter with x.example.com. So we can try to understand, okay, can we put our host in here? So let's try www.example.com or anything else, for example, whatever. It will return forbidden. We can try the same manually, of course, for example.com, it will work. And we can try y.example.com, it will work, and so on. We can try subdomain of subdomains, and it will work. But we don't know the regular expression here that is on the backend. So our goal would be to go to another host. Of course, we could try at evil.com, which is very common. It will return forbidden. So there's some sort of validation about the user input so that the token doesn't get exfiltrated to an external attacker-controlled host. So to use the tool, we just need to basically pass the original input, a valid input usually, for example, x.example.com, or it could be just example.com. We click enter with the default settings. It will basically generate all these possible bytes in multiple positions with all the positions that I was telling you. Somebody's calling a phone on the stage. So we are going to copy this output. We are going to use, for example, burp in this case. We can send to intruder. We can select this part of the request that we want to fuzz. We just need to paste the output and we'll start an attack, okay? So these will send requests. We can order this by status code. So we go down, we can see that it ends around here. It will give 403 after this, and we can try to take a look at some responses that appear. So this is a 302 found. This is not interesting at all. It's in the beginning of the request, but after a while we can see that, for example, this one works, which is x.example.com /2f, which is a slash. It will redirect to example.com, which is not useful, and then we see an actual @ symbol with the percentage 40 in this example. So the @ symbol is kind of working, but it was not working for the @evil.com, for example. Okay, so the idea here is, okay, we are going to pass, for example, this input, and we are going to fuzz it with an @ symbol, and we can put evil.com to see if some sort of variation. I don't know who forgot the phone here, but yeah, let's go. We are going to copy the output. It will fill in all these positions, and then we are going to the intruder again. We are going to paste the new output. And basically, we can try to understand what interesting responses we got here with this @ symbol. And we got only a few. And we got 2f, which is not interesting because it will have a slash. If we go to this URL, it will be the whitelisted domain controlled by the target. This one is not interesting at all. Actually, it will fail. And then we have this one, which is really interesting because we can redirect basically to a host named evil in this case. But we cannot have the dot. So we found a bug in the regular expression on the backend in this demo. So right now, what we can do, especially for those that are used with this, is that, okay, we can have evil here or any other string. So if we can have any other string, we can then just put 123, 123, for example, and this is going to be an host that is a decimal representation of an IP address. So if we just copy this URL, we go to the browser, sorry, not this one, we go to the browser, and basically what's going to happen is we are going to be redirected to this IP address, okay, that can be controlled by an attacker. So we found this edge case that will allow us to leak the token to an external IP address. And it was basically, at the first glance, it was impossible to bypass this regular expression. So this was just like a classical example on how you can use this tool. So let's talk about mysterious bugs. So we want to look literally at anything on the core of a mature target that gets validated, super sanitized, normalized, used in queries, and so on. the more times that you have this input that you can send that is being super validated, the better, okay? So I can recall one example where we could basically only on the sign up, on the front end of this sign up page, basically the email address was being at a regular expression, but that regular expression in the back end was very different. So we could intercept the request and inject HTML into the actual email address. And from there, we could pop basically cross-site scripting, in this case was on Dropbox core, okay? And also in the desktop client, because the same parameter will be rendered in the name of the user when you would send an invite, and in the desktop application, it could be an XSS to RCE as well. So this is more like a methodology with some simple steps. So it's all about setting a goal. For example, ATO, I'm going to show some examples about account takeover. So the idea is about picking a target field that is heavily sanitized. You identify all flows that are going to consume the target field that you picked. And then for every endpoint, you're going to try to find these differences in the regular expressions that are present in the backend. Then we are going to analyze all the responses. You can sort by response code, for example. You can sort by response length and go from there and analyze if there's anything weird happening with this fuzzing that you are doing. And then we can pick a weird byte that actually went through, such as a new line, which is very common. And then you can go through all the flows in that state. So let's say that your user has this very weird email address with an accent in a vowel, for example, and you're not supposed to. If you try, for example, to perform OAuth with that application, maybe the email address will get normalized and two accounts in that state we'll have two different accounts, one with the accent, another without the accent, actual in a vowel, for example, and then somehow, sometimes through different flows, for example, recovery and so on, you can end up in the actual victim email address. This happened with me on GitHub, on many other targets that are super and they have big security teams and so on. And hopefully, in this stage, you just found a mysterious bug, a very weird state where you found like an impossible path to perform, for example, account takeover. If it doesn't work, just go back and try again on a different field. So this is like a methodology that I've been following for the last couple of years, and it's been very successful, not in very small targets, but actually very mature targets that have all these flows from SSO to OAuth and so on. So let's move on to some real-world examples. This is some sort of the example that I gave in the demo with the token, and basically the user will get redirected to an external host, and we want to leak the token from the victim, and there's some sort of validation. But in this case, it was even harder than this. We can just put this evil.com or even just a word or a decimal IP addresses. So now what? So basically, it was just giving 302 for all the possible scenarios to redact the .com. It will ignore just our host if we fuzzed win 1 byte. But with the Recollapse tool, you can specify 2 bytes for fuzzing at the same time. And we got one hit. The semicolon and the @ symbol actually were able to redirect to evil.com again. So sometimes you can fuzz with more bytes in all these different positions and you'll get very weird behaviors. Another example, I was participating in a live hacking event with ZLZ in this case, and he actually posted a blog post because of this issue. We got 40K for it, and basically what we noticed was a null byte on a sign-up request on a target. And the weird behavior that we got with this fuzzing technique was in the response, there was something different on every single request if we would send a null byte in the email or the first name of the account we are trying to sign up. So basically, somehow, a low-level library on the target was handling strings in a bad way, basically. So the null byte was actually being removed and concatenated with the contiguous memory on the server. So if we would sign up as victim, a null byte at domain.com, this would return victim L, for example, at domain.com, and so on. And if we try multiple times, we'll get victim B or victim and some garbage bytes. And we're like, what the fuck is going on? So this was sort of an Heartbleed bug all over again, because we could dump private keys from the region that we were at. It was very regional because we were eating certain servers in the US back in the day. And basically we could dump passwords and all the requests that were being performed by users live. So this was like found just by fuzzing and looking carefully into the weird behaviors in the responses. So very simple, but yet very impactful. Another one, I was calling this in the report recache deception because of using this technique. So we had this endpoint, JSON endpoint that would return information about the user. And I was with Joel, TechnoGeek, and we were poking at this target for a live hacking event, and we were like, okay, let's focus on web cache deception. And we were trying back in the day the classic web cache deception stuff, and we were trying user.scss, PDF, JS, and so on, but nothing was working. I was like, okay, let's try the Recollapse trick again. And basically, we were able to obviously pop it, but basically we realized, of course, all these caching rules are usually regular expression based, or they have some sort of heuristic to check if the response should be cached. Basically, we need to have the correct content type in the response for it to get cached in this case. So let's fuzz it. And basically, what happened is that we first, we had a word list with the extensions, with all the possible extensions known, and then we basically fuzzed before the dot of the extension from 0 to FF with all the possible bytes. And basically, 2 cases returned 200 with the correct content type. With the correct content type being, for example, PDF, with an age 35, Xcache it in this case. So a percentage 23, an hash symbol, or a question mark 3F would basically get cached, but still, it would still return this information about the user with an API token. So what we could do, it was just classical web cache deception from there. We can send a link to a logged in victim that will request this URL, and then as an attacker, we'll just need to access the cached content from somewhere else and steal the API token to perform, in this case, the account takeover, and we could exfiltrate some serious PII of the victim. Another one, username confusion. In this case, this is a very, very simple one, but very, very impactful. So let's say, for example, in any social network, we have our usernames, and our usernames need to be unique. So let's say that the victim is this is the victim, and the attacker account is this is the victim with a new line. So there was a bad regular expression validating the user input, and an attacker could actually have a username with a new line in the end. It was almost the same, but it's actually a different account, and the unique constraint on the database would basically don't do anything. It will allow it because it wasn't being stripped or normalized in this case. So basically, I cannot disclose the target, but let's say that we have an application that allows payments, for example, and the third user wants to send money to the victim. And the way that they do this can be by the username. So basically, a third user that knows the victim will try to send, okay, I want to send money to my friend, but which one? Because they are the same one. I actually changed the pictures of the bunnies here so we could tell the difference on the report, but the victim will be losing money in this case because the third user could pick the wrong person with a 50% chance. So very, very simple one, but yet impactful. But another flow was also affected. Just need sometimes to pay attention to the side effects of such a weird state on the application. As an attacker, if you requested money from the actual, from any user that knows the victim, it appears that Andrea victim is requesting money. And if a third person that is supposed to accept this request clicks on the profile, it goes to the victim's profile, but the money will go to the attacker, okay? So this was a very interesting and very, very simple and impactful bug that I found on the core of an application. Another example, zero interaction account takeover via OAuth. In this case, Shopify. Shopify offers a sign-up login with Shopify OAuth sort of mechanism. And basically, how this works is it's going to send the email address to the target application, and it will check basically if the email sometimes is verified or not. So they have this third-party application. I'm not sure if it was an acquisition or not, but basically, in this case, on the target application, the email address didn't need to be verified to create an account. So we noticed this behavior. We could sign up on Shopify, and then you can create an account, create your shop, but you have limited access. You need to verify your email address. But if you try to log in with Shopify in this state to the target application, it didn't need to be verified. But you couldn't perform account takeover because the email address needs to be unique. And if the victim already owns the actual email on Shopify, you will not be able, as an attacker, to create an account with the same email address. So basically, we tried to change the email address on accounts.shopify.com, which is basically the application where you can change your email address. There was a proper regular expression in place, no new lines, no nothing, no weird characters, no ordinal indicators being normalized, and so on. But then, again, as I was telling you, different flows have different regular expressions most of the times. It's not checked usually in the actual database model as it should on a central place. So by fuzzing the sign-up request on accounts.shopify.com, on actual sign-up flow, we could use this weird I symbol, for example, and it would go through. And the victim at domain.com, in this case, already existed as an account on Shopify core. And then basically we're able to perform the ATO like this. So this is the victim account. He has an account on Taller.app. This is the victim account. We open a new session. We go to Taller.app as an attacker, and it was very, very simple. We sign up with Shopify, and all we are going to do is to put these weird characters in there. Actually, in this case, was the same email as the victim, but with a character that will be normalized in the flow to an actual A. So we just hit create account, and it will just redirect us to the third-party application, and basically we'll end up on the victim's account with no interaction, okay? So this was just another very, very simple example on a very mature target a couple of years ago. Regarding these flows, I wanted to tell you that actually OAuth, SAML, I keep finding a lot of these bugs on these targets because the email addresses or usernames they just flow into the application. And normalization is often used in these flows. So the actual email can contain weird symbols. Even on the domain part, you can have a weird domain to test for this. You can have two domains, one with a weird A that is going to be a punycode domain and your actual domain. And then you can test the scenario where an attacker can create a fake weird punycode domain that can be normalized to the actual domain. So it opens the door to these normalization flow, especially with SAML, OAuth, and so on. And it's very common to have straight up email verification bypass. Why? Because developers implement OAuth before they move into SAML on these big enterprises. And usually OAuth, like login with Google or Apple. Google and Apple, they validate the email address, right? So you create an account and you'll be able to log in with Google or Apple on any application because your email is verified. You have a way, they have a way to verify your email address that will be super big. If you had an email verification bypass, for example, on Apple, you could just take over lots of accounts in lots of applications, right? But then the developers move on, okay, we need to implement SSO because we have this big customer and we need to have this. And there, the developers will be used to trusting the OAuth provider, and they will be starting trusting Okta, for example. And the thing is, there's no guarantee that an account on Okta belongs to an actual email address because there is no email verification for that. I mean, we can configure these SSO providers for that, but the thing is, even the organization or the IDP sometimes cannot be checked, is not checked properly, okay? Let's say that an organization configured SSO on a given application, and then basically there's another user, a malicious user that configures SSO on their end on the same application. If the attacker can create, basically, they'll configure SSO and they'll try to log into the application with a new user with an email that belongs to the other organization. Sometimes you'll end up on the target organization. This case is very rare, but it happens sometimes. Another final example, which is also a zero interaction account takeover in the recovery flow. So the target in this case is an email provider. So it was big to actually perform this ATO with big impact because we're talking about an email provider. So our goal was to account takeover with zero interaction, an inbox that was configured for us. And people were able to sign up as username at target.com or use their current email address to create an account. So this was an email provider, but you could use your current email address. So let's explore all the flows in this case. So we tried, so the victim at target.com existed as an account on the target, and our goal was to retrieve to access the email inbox. If we put the victim at target.com on the recovery flow, it will show up, okay, we'll send a code to a redacted recovery email address. So as an attacker, we could add the email of the victim as basically our recovery email. This will require email verification, but it changes it results in a change of the previous flow of recovering victim at target.com. After we do this on our end, it will end to a weird state where we may have a logic bug. So basically, it results in this change of flow where when we attempt to recover the victim, it will show the email itself, which makes no sense, like I'm trying to recover this actual email address of the victim. It showed, oh, you want to use this email address to recover it? It makes no sense, because before it appeared just like this. So as an attacker, we introduced some sort of confusion in this state. So there was some sort of regular expression, again, matching the target, the actual email provider domain. Because they wanted to be able to distinguish both types of accounts, the ones that they will be creating an inbox for, and the others that already have an inbox, an external provider. So after fuzzing, we realized that some special characters were displaying when we put an email address like this. We were getting the exact same behavior, and this was basically super weird. So we were thinking, maybe the regular expression doesn't have a null an assertion on the end of the string with the $sign. So, and I was correct, because if we added a recovery email address as victim@target.com.domain.com, the regular expression will match target.com and basically will show up as a recovery email of the attacker's account. And the option, as option 2, we still have the original recovery email address. So we click on recover to this email address, and basically what's going to happen is we recover a code, and then the application will ask us, okay, do you want to log in into the victim's account or the attacker's account? So this was a logical bug, and also this .domain.com, I was able to configure an email inbox on that subdomain as the main domain of my domain, and basically I was able to take over the account bypassing 2FA and so on, and they paid me $50K for it back in the day. So it was huge. So to sum it up, in terms of developers, we should test and fuzz our regular expressions. Even if we rely on well-known libraries, you see that there are some weird behaviors going on. One of the major takeaways here is that very simple input modifications can result in great impact by flipping or adding new bytes and all the possible combinations. For those of you that are starting to poke on very mature targets, I heavily recommend for you to try this. And also, if you are trying to attempt some bypass of a sanitizer or a firewall or a WAF, I recommend that you try the Recollapse tool and try to see the results. I have some people that I've been reaching out for in this year, saying that they have been quite successful. And also, this black box regular expression testing is still not very touched. I keep finding all these issues when I go to live hacking events, for example, with HackerOne. It's always there. So it's very creative and manual work. You can use this tool, you can do the manual fuzzing, you get the idea, just go for it. And finally, the regular expression behavior can also reveal information about programming languages being used in the case of the new lines that I showed you. So basically, if something is being validated and you can bypass it, think about the impact and you'll see the big picture. And basically, if somebody says that something is impossible and it's not bypassable, we are hackers and we always find a path to do things. So I'd like to thank these people that collaborated with me. I couldn't list everyone here, and that's it. If you have any questions, let me know.